I will wait for a couple of minutes and let people join, and I will start. Regarding the exam format, actually, I am not sure. I think you have got a mail for that, like how the exam will be conducted. Uh, Let me check this here. So it is written a type of the questions may include multiple choice questions, fill in the blanks, essay type answers, etc. So it can have like all three options. I'm guessing it will be similar to the assignments given, but I'm not sure. So these options are given. So you have to check whether your exam is computer based or paper based. So type of exam will be available in the list. Okay, so this will be a pen and paper based exam. Right. Okay, for pen and paper based exam, nothing is written, so you have to write the answers on sheets. So there may be short and long questions also. Okay. So if you have further question, then you can write in the discussion forum maybe, like regarding the exam format. Okay, I think we can start now. Any other question? Okay, offline exam. Yeah. So for offline exam, no like format is given. So I think it will depend on the instructor. Uh, but you can like write this question in the Q&A or discussion forum for that. Maybe they will be able to guide you, like the NPTEL support team. I'm not aware of that exactly. Okay, so let's start the session. I will introduce myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. So this is week 12 for this course, Semiconductor Device Modeling and Simulation. So in this week, mainly simulation part was covered. So this session will be a more like a theory questions, not many numericals, because the topics those were covered are mainly theoretical. Some examples were given how to use those tools, simulation tools, but I will not go into details of those tools. I will mainly focus on some theoretical questions. So similar to the questions, those are in the assignment 12. So in this session, like unlike the other sessions where I solve the numerical, I will try to give the problem first and then you can think of it. If you are watching this on YouTube, then you can take a pause and maybe think about what the answer will be. And if you have gone through the lecture videos, then the questions will be easy, like you will be able to give the answer. So the idea for this session will be mainly the revision of what you have learned in this week, not much on problem solving. I hope my screen is visible and I am audible. If there is any problem, then you can let me know. It is difficult to go out and check the chats when I'm in presentation mode. So you can unmute and speak. Okay. So let's start with a basic question. So this topic was about ticket simulation tools. So the question is, what is the full form of ticket? Okay. So what is the answer? So what ticket stands for? So it is technology, computer aided design. Okay. So these tools we use to design our experiment or design our device or design our circuits or systems. Okay. So what ticket tool, those were that was discussed mainly in the lecture series, that is like Silvaco, Atlas Silvaco. Okay. Next question is, what is the hierarchy of simulation tools? Like in which order simulation tools are used? So I will give few options. First option A is device simulation. So the tools those are available for device simulation. Next is circuit simulation. Then process simulation. Next option is, first is circuit simulation, next is device simulation, last is process simulation. Option C is process simulation, next device simulation, and then circuit simulation. Option D is circuit simulation, next is process simulation, third up device simulation. Okay. So what will be the answer for this question? So the answer is option C. So the simulation tools are used in this order. First process simulation is done, then the device simulation, and then the circuit simulations. So the process simulations is basically based on what we can achieve, like what doping concentration we can achieve, what dimensions we can achieve. So based on that we make the device, because if we do the device simulation first, we may like get some parameters which we actually cannot achieve physically. Like for example, if we cannot get doping concentration very high. For silicon, the density is in the order of 10 to the power 22 per centimeter cube. So we have to be like, the doping concentration should be much less than that. We cannot get like doping concentration close to 10 to the power 22 or more than 22. So these limitations, what limitations we have in our processes, that we have to know first, and then we go for device simulation, and based on whatever the devices we have, what device we can achieve, based on that we design our circuit or system. Okay. So I hope it is clear. Let me go to the next question. So question 3. In this question, few statements are given, and then which statements are correct. So the statements are, first statement is, as I mentioned earlier, this will be like a more like a theoretical session. I will discuss some of the questions like MCQs. So you should think about it like while I am writing the question. Okay. So there are few statements given in this question. So first statement is, Atlas is a framework program. that integrates several smaller programs. Into a complete process simulation tool. Next statement is Atlas is a physically based 2D and 3D device simulation tool. Next statement is Athena is a framework program that integrates several smaller programs into a complete process simulation tool. Last statement is Athena is a basically this statement instead of Atlas I'm writing Athena. Physically based 2D and 3D device simulation tool. Okay, so what is the answer? I hope you all can were able to give the answer for this question. So here what are the statements which are correct? So the correct statements are so Atlas is a device simulation tool. Okay, this has been discussed in the videos by the course instructor Professor Vivek Dikshit. So this is a device simulation tool, Atlas, and Athena is a process simulation tool, right? So the statements 2 and 3 are correct. Try to think about the answer along with me, then only this session will be useful. Let me write the next question. So question 4. So the device simulation tool that was used for the course is Atlas Silvaco. So this question is on that. So in Silvaco, mainly in Atlas, electrode is a statement. So the statement is written like this. And it is used to represent the structure specific group. Okay, whether the statement is true or false, that is the question. So whether the statement is true or false. So the answer is the statement is true. Electrode is a statement that is used to represent the structure specific group. Okay. And what other statements? Those are used to represent structure specific group. So other statements, if you can recall. So what are the other statements? So there is one statement called mesh, another it is electrode, reason, doping. Okay, so these are related to structure specific group. So the commands which are divided into different command groups. So in the structure group, these are the commands used, or these are the statements used. Okay. So I think one example was discussed in the class, like this example. So this is the structure group. Okay. So in this example, all these commands like for mass, region or electrode, so these are the commands for the structure. That is why it is classified like that. And then after that it comes the model and then the other method and result analysis commands. So you should remember at least these different command groups and all these statements. We go to the next question. So again in this question there are few statements. I will write those first. So first statement is input syntax is case insensitive for Atlas. Next statement is input syntax is case sensitive for Atlas. The third statement is inputs syntax is case insensitive for tech build. Third statement is again case sensitive. Okay. So the options are for this question. So there are 4 options. Only, statement, one and 2 are true. The next option is, you can think about the answer while I'm writing the options. Only statement 1 and statement 3 are true. Option C is only statement 2 and statement 3 are true. Last option is option D. Only statement 1 and statement 4 are true. So what is the answer? So case sensitive and insensitive mean the statements we write in these softwares, whether like the same word with different cases are treated as different word or not. Okay, so in Atlas the syntax is like whatever you write, that those are case insensitive, whereas in Dagbill, so which is a GUI tool, so here the input syntax are case sensitive, so the correct option is D. Okay, you have to be careful while using these softwares, like how you are using the input syntax. Let's go to the next question. This is a fill in the blank question. Okay. So the question is, Atlas can read up to dash characters on one line. The slash character at the end of a line indicates dash statements. The options are A 256, continuation of long input. Option B is 256, end of input. Option C is 128, starting of input. Option D is 128, skipping the corresponding line. what is the answer. I will take a pause here. You can think, and if you have gone through the lecture, then this question is easy. So if you remember it correctly, you can tell the answer. Okay. So I hope you already got the answer. So answer here is A. 256 characters. Atlas can read up to 256 characters in one line, and if the line is long, then the slash is used as a continuation of long input statements. Okay. So using this slash character, a long input statement can be spread over several lines. Okay. So this is question 6. Let's go to the next question. Structure files can be plotted by using dash in Atlas. The options are Tony plot. Option B is system plot. Option C, print plot. And option D is out plot. I hope you already got the correct answer. So here the answer is A. Structure files can be plotted by using Tony plot in Atlas. Okay. So this is Tony plot. This is in the common group result analysis, right? This is for result analysis. What I have written. So what other statements? What are the statements in this command group? First one is extract. And another one is tonic plot. Okay, these two. So using this command, what can be done? We can basically plot different parameters, for example like area concentration, doping. Okay, so what we use for example, carrier concentration can be plotted. Okay, so again this question, so it is already mentioned in the lecture, so you can see here again. So this question is again from the slide, so you should remember this statements. Next I will discuss few questions that is related to, like, so these questions are like theoretical questions related to the tools. Next I will discuss few questions, those are like bit general, how different models and how the concepts that we have already learned, like we have already discussed about drift diffusion, we discussed about mobility, so how we use those in the simulation tool. So the next question is, bulk mobility modeling can be separated as. So the first option is low field mobility for bulk or inversion layer. Next is low field mobility to account for velocity saturation effect. Next statement is smooth interpolation between low field and high field regions. Next statement is high field mobility to account for velocity saturation effect. Last statement is high field mobility for bulk or inversion layers. Now again, few of these statements are correct here. So the options are only statement 1, 2 and 3 are true. Next option is only statement 1, 3 and 4 are true. Next statement is next option is only statement 1 and 4 are true. Next option is there are too many options. Okay. Only statement 2, 3 and 5 are true. So last option is only statement 1 and 3 are true. So this question is on mobility and basically how the mobility models are used in simulation tools. Okay. So what will be the correct answer for this question? So the low field mobility that is used for bulk or inversion layer uh, and high field mobility is used for that is used to account for velocity saturation effect. Okay. And so I will discuss it here. So in general, the relation between, we know that the drift velocity Vd is equal to mu into E, electric field. So like if we take Vd by E, so that is basically mu. But what happens practically is that if this is our electric field and this is drift velocity. So initially, due to electric field, drift velocity increases. After a point, it becomes constant. This is the velocity saturation effect. So the velocity is constant. Now the mobility is given by the slope here. So slope in this region. Okay, that basically gives mobility. We cannot define a slope here because it's a constant. So in this region, the concept of high field mobility that is used because the basic definition of mobility is not valid for this region. And in here in this region, uh, so it's like a two different region, and then in this region it is joined using a smooth curve. Okay, so here the answer is low field mobility accounts for bulk or inversion layer, and high field mobility used for velocity saturation effect, and smooth interpolation between low field and high field region. Okay, that is how the mobility modeling is done. So what are the correct options or statements? So 1, 2 and 1, 3 and 5. So option is B. So the total mobility modeling is separated. Okay. Is separated into three different regions. So first one is the low field mobility. This is in this region, that is in the bulk and inversion layers when the electric field is less. Next is the high field mobility. In this region, right? And third is the reason between these two, like reason that here a smooth interpolation is done between low field and high field region. So I have already discussed in earlier sessions about this concept, and I have already discussed how the mobility is affected by different parameters. For example, uh, it depends on doping concentration or depends on temperature. So those were already covered. So while using the simulation tools, these are the things we have to be remembered, like the doping concentration, like the mobility values are very different for two different doping concentrations. So what you are using for your simulation, you should use the appropriate values according to other parameters so you are using. I hope everything is clear and there is no question. check if this. Let's go to let's go to the next question. Again, there are few statements. I will write those down. First statement is, for radiative recombination, an electron loses energy on the order of the band gap and loses energy on the order of the band gap and moves from the conduction band to the valence band. Next statement is, for optical generation. So this question is on like excess carriers basically. For optical generation, an electron moves from the valence band to the conduction band. Next statement is, for radiative recombination, an electron loses energy on the order of the band gap and moves from the valence band to the conduction band. The last last statement is for optical generation, an electron moves from the conduction band to the valence band. Again, there are few options here which statements are correct. So first option is, I'm writing down the options. You can think about it by reading these statements, which are the correct statements. Only statement 1 and 2 are true. Statement option B, only statement 1 and 5 are true. Option C, only statement 3 and 4 are true. Okay, there are too many options for this question. Option D is only statement 3 are true. Again, we have more options. Option E is only statement 1 is true. This is E. Option EF. Option EF is only statement 4 is true. Last option is only statement 2 are true. So what is the correct option? So what happens in optical generation and radiative recombination? Okay. So suppose this is the band diagram. I'll use the black color. It is disturbing, otherwise red to the eyes. So this is the band diagram for a particular material. This is the conduction band edge and this is the valence band edge. So if a electron moves from here to here, EC to EV, then it will emit energy and that will be equal to the band gap. So when an electron moves from conduction band to valence band, okay, so uh, this is basically a recombination process, right? So in a recombination process, the electron loses energy, which is equal to the energy of the band gap, Eg, and it moves from conduction band edge to valence band edge. Okay. So the first statement for radiative recombination, so there are two types of recombination, radiative and non-radiative, like whether it is emitting a photon or a phonon. So for radiative recombination, the electron loses energy on the order of band gap Eg, okay, and if if this band gap energy is equal to the energy of a photon, like which corresponding wavelength, so Eg is, if it is equal to h nu or hc by lambda, so we can calculate lambda, and if this lambda lies in the visible wavelength range, so that is 400 to 700 nanometer, then the electron will emit like a photon of some color, okay. So that is how the LEDs are made, so optical devices are made. So in this kind of recombination, electron loses its energy in the order of band gap, and it moves from conduction band to valence band. So this is the radiative recombination process. Next, what happens for optical generation? An electron moves from valence band to conduction band. So this is a generation process. So generation means generation of electron hole pair. So in optical generation, an electron moves from valence band to conduction band. So these are our two options. So what happens in optical generation? Suppose this is a material, this is EC, this is EV, and some light is incident on this material. So this is photon, right, h nu. It has certain energy, and if this energy is equal to or larger than the band gap of the material, then this photon will excite an electron from valence band to conduction band. So this is the generation process. So this is recombination. So, and this is generation. Recombination and generation of electron hole pair. Okay. So I am considering this as a direct band gap material. That is why this is a radiative recombination process. So this question is about on that. So the correct option for the this question is option 1 and option 2 are correct. So option is A. Okay, so our answer is A. So I hope this is clear. Again, this is for direct band gap material. For silicon, if you recall it, if you can recall, so silicon is an indirect band gap material, and for silicon we have the generation, the recombination process is trap assisted or defect assisted, and it is also known as Shockley-Hall rate recombination process, SHR recombination. I hope the question is clear. Is there any doubt? I will take a pause here. There is no doubt. Let's go to the next question. So there are few questions I have made, like based on the lecture videos I have also gone through this week. So I have few more questions on that, like theoretical questions. This question is on like empirical modeling. So I'll write down the question first. Empirical modeling is used for dash level modeling. I will give you the options, then you can get then you can I hope you can easily get the answer. Okay. First option A is device level modeling. Option B is circuit. Option C is circuit and system. Option D is device and system. So these are the options. What is the answer? Just give me a minute. Okay. Sorry for the disturbance. So what is the answer for this question? Empirical modeling is used for dash level modeling, whether it is a device level modeling, circuit level, or circuit and system level modeling, or device and system level. So what do you think? First of all, what is empirical modeling? So in empirical modeling, this is not like exactly physics based modeling. So this is mainly based on observations or experimental data. I hope I'm unmuted. So the empirical modeling is not exactly physics based modeling, not exactly analytical modeling, and it is mainly based on observations and based on experimental data. Okay. So this is used not for device modeling. This is mainly used for circuits or system level modeling. Suppose we have a system. We give some input and we take some output, right? And based on how the relation between like input and output, based on those experimental data, we try to define this system. So this is like a black box for us initially. Okay. So for circuits and system, like for this kind of a system, we use empirical modeling. So this is useful instead of considering what is the physics behind the of all the devices that is inside the circuit or system. If the system is very complicated, then our analysis will also be very complicated if we want to do everything like physics based. So in that case, empirical modeling can be useful, and this is often used for circuit and system level modeling, circuit and system designs. Okay. So here correct option is C. So I will write down whatever I have like said. So empirical modeling is based on observations slash data. Okay. I mean experimental data, or after characterization what it is kind of result the system gives, rather than physics. Okay. So this is often useful to describe the behavior of a system, behavior of a circuit, like the overall how the system will behave. Okay. So the way people do the modeling of device and circuits and system, uh, so the approaches are different, like it can be different. For complicated design, empirical modeling is often preferred. Okay, let's go to the next question. I hope I am like audible. If there is much background noise or any disturbance, let me know. Okay. So next question. This is actually from the last week. So I wanted to discuss this question, but like the session was already over. So I'll write it here. Uh, but this question is on quantum mechanics from the topics of the last week. Okay. Which of the following statements accurately reflects the relation between, so uh, the position and momentum operators and the Heisenberg uncertainty principle. So you know what non-commutative mean, okay, in like maths, what non-commutative means, of position and momentum operators and the Heisenberg uncertainty principle. So I will write the options, then the question will be more clear and you will be able to answer. So the non-commutativity of the position. So position operator is denoted, so if it is a position in x, if I'm considering only the position in x direction, so this is denoted like this. I will use these shortcuts to write down the question. And momentum operator is, momentum is denoted by p, so I'm writing px. I'm only considering one direction. Okay, the non-commutativity of the position and momentum operator implies that it is possible to know both the position and momentum of a particle, of a quantum mechanical particle, with arbitrary precision. Next option is the non-commutativity of position. I will write the directly operator, the position and momentum operators implies that the particle have for which we are considering the position and momentum an inherent uncertainty in their position and momentum that cannot be reduced. Okay. Next option is, so let me write this Heisenberg uncertainty principle. I will use a short form, Heisenberg uncertainty principle, say. Okay, so Heisenberg Heisenberg uncertainty principle implies that implies that I hope my handwriting is okay, like can read. Is that particles have an inherent uncertainty in their position and momentum that cannot be reduced. But this uncertainty is not related to non-commutativity. Of the operators. Of the position and momentum operators. Last option is the Heisenberg uncertainty principle is a consequence of the non-commutativity of position and momentum operators, which implies that it is impossible to know both the position and momentum of a particle with arbitrary precision. Both position and momentum with arbitrary precision. Let me take a pause for a minute here and should read the statements and think what is the correct answer. Why I'm saying this? Because the statements look similar, but there is a certain difference. So this question is I believe it's different. This question is on Heisenberg uncertainty principle and position and momentum operators. Okay, position and momentum operators. Another term that is important here is the non-commutativity. Now, you all know the Heisenberg uncertainty principle. Like this, you have studied earlier also. So what we know, according to Heisenberg uncertainty principle, we cannot determine the position and momentum of a particle precisely. Okay, so what that means, if there is a like if the deviation in the position of a particle is delta x, and deviation in the momentum of a particle like px, so you have to consider this like if you are considering x direction, and momentum is in that is also for px. If you are considering in y direction, so that in that way you will consider delta y and delta py. So we know that this uh, this two difference is, and if we multiply it, this is in the order of h bar. So the exact number is h bar by 2, but the important thing is that it is in the order of h bar, which is the reduced Planck's constant, and you know that a value for reduced Planck's constant is 1.06 into 10 to the power minus 34 joule second. Okay, so this is a very small number, but we can still say that there is a certain deviation. Like we cannot exactly determine what is the position of the particle, and we cannot exactly determine what is the momentum of the particle simultaneously, like at the same time. Because when we try to measure these properties, we actually disturb the whole system, the system of the whole particle. So that is why it is impossible to measure position and momentum with arbitrary precision. That is what Heisenberg uncertainty principle says. Now, what it actually arises from? So here the term given is non-commutative. Okay, what commutation mean in maths? So if a plus b is equal to b plus a, or if x multiplied by y is equal to y multiplied by x, so this means this is the commutation, right? Now, what is commutation for quantum mechanical operators? So if you operate the operator on wave function, so this is the position operator and this is the momentum operator. So if you operate these operators on the wave function, if the order does not matter, like if you first use the momentum operator, then the position operator, or if you use the first position operator, then the momentum operator, if the final output does not depends on the order, then these two operators are called as commutative. But these two operators are actually non-commutative. Okay, you can, so for position this is simply multiplied by position x, and for px it is minus, so h bar by j, I'm not sure whether it is plus or minus, but this is delta x. Okay, so and you can use these operators on a wave function, okay, psi of x, and you can see whether these operators are commutative or not, but these two operators are not commutative. So when the two operators are not commutative, then only this uncertainty principle arises. Okay, So this is true for any two quantum mechanical operators. So uncertainty principle is true for any two quantum mechanical operators if those are non-commutative. You can check. Okay. So what is the correct option? Actually, the Heisenberg uncertainty principle is a consequence of non-commutativity of position and momentum operators, and it implies that it is impossible to know both position and momentum with arbitrary precision. Now there are other operators also, other quantum mechanical operators also, which are not commutative. For example, energy operator. I'll write here the answer first. So answer for this question is D, right? So another set of operator is energy operator and time. So these two operators are also non-commutative. So the uncertainty principle is true for these operators also. And I will give the proof for this like quickly. It's a very simple derivation. So first I will write down the statement: if two operators are non-commutable, what I am writing, okay. Then it is impossible to determine those properties precisely. Okay. Those properties means we use the momentum operator on wave function, we get information about the momentum or average momentum or mean momentum, or if we use position operator, then we get the position operator on the wave function, we get the position, the mean position. Okay. So what like there are sets, I'm already mentioned, position and momentum, these are non-commutable, and or energy or time. Okay. Now we already know, we are familiar with uncertainty principle that is related to position and momentum. So delta px is, and delta x is in the order of h bar. I'm not writing exactly equal. Okay. So similarly we can say that delta E multiplied by delta T is also in the order of h bar. Okay, energy and time. Now this is a very simple derivation. We can do this from this expression. So delta px by delta t, let me write it this way. I will multiply delta x here and delta t. So this is h bar. Next is delta p, momentum by time. This is actually force. Okay, into delta x multiplied by delta t. This is in the order of h bar. Next, force into x. So this is like distance. So that means energy. So this is delta E multiplied by delta T is in the order of h bar. So we get these expression from starting from this well-known Heisenberg uncertainty principle for position and momentum operators. Okay. I hope the question is clear and there is no other doubt here. Now we have some time. Let me discuss few more questions. Now I have mentioned about, I don't have the exact questions for this. I am just giving you the idea. So we have discussed about the mobility model, like how the high field and low field mobilities are determined, how those are used in simulations. Now there are various mobility models which are available. Okay, those were discussed, those were mentioned in the lectures. So there are few classifications of these mobility models. Now which class is used in which scenario? Okay, so this question is on mobility models. Now what are the classifications for this? There are three classification: physics based or physical based model. Another classification is semi-empirical. What is empirical model? I have already mentioned. So semi-empirical, this is completely physics based, and another type of mobility model is empirical. Now, in which scenario these models are used? Now, the physics-based model, how the mobility is actually varying, or how the electrons and the carriers are moving. So the exact mobility, that is the physics based model of the mobility, that is not uh, that is not used in many scenarios. Like, it is very difficult to exactly determine how the carriers are moving. So you know that the carriers will be scattered, it will go in different directions. So overall mobility modeling using physics based method is rarely used. So this is rarely used. And if we try to actually model mobility using like a completely physics based model, it may not agree with the experimental data. Okay. Now semi empirical model, that is often used. So there is some kind of like power law dependency, and empirical models, those are used when like it is not physics based, not completely physics based. This may mainly based on the observations, and these are valid only for a specific region. Like if you are doing the simulations for a very specific application, or with very specific conditions, then only these models are valid. Okay, so it has narrow range of validity. Next, few topics those were discussed in the lectures are the like what kind of model should we use for what kind of simulation. As I mentioned in the last week also, like when we are considering very small dimensions, if it is in few nanometers, then we have to consider the quantum mechanical effects. Okay, so if we are simulating like nanostructures, so let me frame this question like this. What model, I'll say models, is used for simulation of nanostructures? Okay. Nanostructures means the dimensions are in few microns in any one or more than one directions. Like if all the dimensions are in the nanometer range, then it will be like a 3D nanostructure or quantum dot, or if it is uh, in two dimension, if the structure has like dimensions in nanometer, then it will be like a quantum wire kind of structure. And if in only in one direction, if the dimension is in nanometer, then it will be a nano sheet, like a 2D material kind of structure. Okay. So what model is used for simulation of nanostructures? I'll give few options maybe. So drift diffusion, next option is hydrodynamic, next option is Monte Carlo simulation techniques, last option is Schrodinger equation, or Green's function method. So I mentioned in the last session also, when the dimensions are very small, we have to consider the quantum mechanical effects. So drift diffusion model and other things actually not consider uh, those like quantum effects. So to solve the this kind of structure, to solve the properties in this kind of structure, we have to start from Schrodinger equation, because these structures are in like nano dimensions. The dimensions are in nanometers. So for this very small dimensions, we generally use Schrodinger equation. Okay. Schrodinger equation or Green's function method. Drift diffusion model is valid only for like bigger structures like old ICs, and even for modern ICs where the dimensions are much smaller, in those cases also either hydrodynamic model is used or Monte Carlo based simulations are used. Okay. Let's see. Okay, that's all from my side. I don't think I have more question. If anyone of you have any then you can ask. uh, I tried to cover like maximum theoretical question. Those can be there for this week, like for this week 12. uh, so how the mobility like is considered in simulation. uh, so as I have mentioned, depending on the scenario, mobility can be different, it can vary a lot. So based on the scenario, what kind of mobility models are used, those were given in this lecture, so you can take a look of it. You can see that like how many models are there, like there are so many models. So those are used for specific purpose. For example, this is for 300 Kelvin only. Okay, so during simulation you have to be careful like what you should use. Okay, so if there is no question, we can stop the session here. Regarding exams, you can ask them directly or send them a mail, because I am not aware of the pattern actually. Okay, because it is an offline exam, it will depend on the instructor. But I don't think the question will be very different from the questions those are there in the assignments. I'm not sure about the format though. So I'm only dealing with the problem solving sessions. Okay. So if you have few more doubts, then you can ask in the Q&A or discussion forum for this. Okay. So if there is no question, you can like before exam, if you have some doubt, you can reach out to me through the like discussion forum. Uh, if there is no question, then I will stop the session here, and all the best for the exam. Thank you everyone.